So I want to look at some properties of trees. So we're going to consider a few theorems related to trees and maybe a couple of new definitions. But on this particular part of the video, I want to consider the following theorem, which is numbered 50.4. Let T be a tree, and for two vertices out of the vertex set of T, we claim there is a unique path from A to B. So one of the special properties that a tree has is the uniqueness of any path from A to B. Okay? First of all, we know T is connected, which means that we are guaranteed there is a path. That's going to be the first part of my proof. But the main point that I want to prove here is that it's unique. When a graph is a tree, any path from one vertex to another is necessarily unique. Also, if you take any graph G with the property that every vertex has a unique path from one vertex to another, then G is a tree. So this property is actually a defining characteristic of a tree. So if it's a tree, then there's a unique path from any vertex to any other vertex. If it's a graph that has the property that given any two vertices, there is a unique path between them, then that graph has to be a tree. Okay? All right, so let's prove this. First of all, let's go the forward direction, which is really just everything before my also statement. Let's let T be a tree and AB be any two vertices out of the vertex set of T. First of all, is there a path from A to B? And the answer is yes, obviously, because T, by definition, is connected. All trees are connected. Then there exists an AB path. Now, the next question is uniqueness. So we're going to follow an approach that was given in an earlier proof template in an earlier section. To prove uniqueness, we're going to assume there are two different ones and show that leads to a contradiction. So assume, for the sake of a contradiction, that there exist two paths from a point A, or vertex A, to vertex B. I'll call the two paths P and Q. So let's say my 2 points are here, somewhere in the graph T, or in the tree T, and there's a path P from A to B, and there is a path Q from A to B. Now P and Q may overlap, but since they are different, they must diverge at some vertex somewhere in the graph, like right there. Okay? So if I were to start at P and start at A and follow P all the way to B, and then follow Q all the way back, you may think that looks like a cycle, but because you repeat all the vertices that may be inside here, it's not a cycle. I don't know if I made that very clear on the last slide, but a cycle only repeats the first and last vertex. No other vertices must be repeated. So this, if that forms a cycle, then we're done, because that's a contradiction. T can't have any cycles in it. But I claim we have to be able to form a cycle somehow if we say that there are two distinct paths from A to B. Okay? So, we can make a cycle, which would mean that we have a contradiction. If there is a cycle inside my T, then it's not a tree, which would be a contradiction. So, assume that P starts at A, travels along to, let's call this point right here X, and then goes up this direction as a Y, and it follows all the way to B. So let's say that this is what the path P looks like. And Q would start out the same, since it's going from A. Let's say there's some overlap for a while, but once we get to X, then we diverge off in a different direction. So we say we go off to Z and follows along till I get to B. Okay? So right here is the overlap. That's this portion of the graph in red right here. We'll call that the overlap. Now consider the graph T t minus xy. So I'm removing the edge xy from t. Start at x on the path P, and let's follow P inverse until we get to A. So we're going to follow that path from X to A. Then we're going to jump over to Q, and we're going to follow A all the way to B. So then follow Q from A to B. Then follow P inverse again from B to Y. Now, we don't have this edge in there because we're talking about t minus xy, but what we just found was a walk. It's not a path because we repeat all these vertices in here, but you found a walk from x to A all the way to B, and then B back to Y. So there's a walk from X all the way to Y that doesn't need the edge XY. Now, because there's a walk, then that means there's a path. Remember, there's a theorem that says if there's a walk, there must be a path. A path is a walk that doesn't repeat a vertex. We don't know what it is, we just know it exists. So there is an xy path in t minus xy, since there is an xy walk in t minus xy. So we're going to call that path r, and then if we add xy to the end of r, then that means we have a cycle, because we go from x all the way to y, and if we add xy, that means we've now gone all the way back to x, which means there's a cycle inside t. There's a path from x to y in t minus xy, and if we add xy to it, then there's a cycle inside t. And that's the contradiction, since trees don't have cycles, which means that we've proven that there can be one and only one path from A to B. There exists a unique AB path, proved. Now, for the stuff that comes after the also, I'm going to leave that as a refer to the text option, so I'm going to omit that.